And we should be a go. So I want to thank everybody for joining us for one of the Siemens webinars. Today we're going to delve into the world of G-code setup and programming on a B-axis lathe. So for those of you that maybe have joined me in some of these in the past, you may have seen I did a series of these webinars from the shop turn perspective or the conversational program perspective. We started at a simple lathe and we went right all the way up to a multi-channel lathe, B-axis turning, all that good stuff. So then I've been slowly paralleling the series from a G-code perspective. So today is getting into the B-axis turning segment of that series. So we're getting pretty high up in the advanced technology. And then following this, I will do one, hopefully sometime this year, getting into multi-channel programming from a G-code perspective. All right, so let me introduce myself for those of you that may not already know me. My name is Chris Pollock. I am the manager of our Virtual Technical Application Center for Siemens. So basically what that allows me to have the privilege of doing is creating a lot of our online content, certainly centralized around operation and programming topics. So I am a resource for you, whether you're a OEM, dealer, end user, by all means, if you have any questions from an operation and programming perspective, feel free to reach out. Probably the best way to get a hold of me would be via email. Sometimes it's a little crazy, as we all know these days. I've been doing this online stuff for a lot of years, and it just kind of happened to fall in really well with our current challenges, right, with everything going on. So certainly we've been busy from the online perspective for sure. So I'm here as a resource. By all means, reach out. I always love to plug what we got coming up. I've been dragging a lot of my colleagues in to do guest appearances, but today you're stuck with me. You're not going to have a guest host today. But our next one coming up in December, which is going to go into the world of structured programming, which is pretty cool. If you don't know what the term structured programming is referring to, it's basically using variable-based programming to create intelligence in your part program. So if you're jumping from mains to subs and back to mains, the part program will always know where you were last at. So if a program is aborted midstream, you can always start the program from line 1. You don't have to worry about the operator figuring out where it was last at within a feature, and the program will jump to that portion of the code and continue cutting. So it certainly allows things to get much safer. In the past, it's been used in high technology lathes, like multi-channel lathes, but we've been using it in mills, 5-axis, 3-axis. Really, once you adopt that main program, sub-program structure, then this concept of structured programming really becomes quite powerful. So check it out. Danny Vitullo will be hosting it, and I will be emceeing, so you'll still get to hear my pretty voice a little bit. All of our content does go online. As I mentioned before, we record the content and we will post it. So if you're looking for our material, or you want to see what's coming up next, or you'd like to get to our library, by all means, go to our CNC4U website, or you can drive directly there by the CNC webinars link. But either way, you get to there, you can click the webinars, see what we have coming up, certainly get an entire list of the previous webinars that have been hosted before. Additionally, you can also go to this training class section, and here you can see classes that we have coming up, but we also have this virtual training tab. So what I would encourage is go to the virtual training, click on that link, the Sinumerik CNC Content Manager, because what we've done here is I've built an Excel spreadsheet that really has all of our online content and has direct links to each of them. So whether they're on CNC4U or on our YouTube channel, you can use the top little selector, and you pick some of the interest levels, whether it's the product or the technology, and the document will automatically highlight which ones you should look at. So this thing's really handy for navigating. We get a lot of material. I think to date, we're probably 80 plus videos online. So check out, download, and don't just download this once. We update it periodically, maybe twice a year, 3 times a year, somewhere around that. So I would say if you haven't downloaded one recently, go grab it. It's a good thing to have if you're doing a lot with Siemens, with our product. And then additionally, I mentioned our CNC for You channel. So, or shall I say our YouTube channel. So if you're not familiar with it or haven't been over there, we do have a YouTube channel we refer to as Mr. CNC. We have pretty much all the webinars are there available as links to see right on YouTube. But we also do a lot of how-to videos. I have a YouTube live segment we call Simply Sinumerik Live. So if you haven't checked it out in the past, please, by all means, navigate over to the channel. And if you like it, please follow it and share it. Once we see that kind of activity, it makes it easier for us to continue to promote and explore these different avenues of reaching out to the public, right? So that's kind of what we've been doing here. All right. For whatever reason, my Q&A window got hidden behind another one. All right, let me minimize this stuff. Give me 1 second. Okay. So let's get into the primary topic. Enough of the precursor. We got a lot of material to kind of run through today, so I do want to kind of drive right into it. So in the past, a lot of the material we've done has kind of transcended a few different controls. We have a lot of commonality in programming between an 828 and the 840. Even some of the 808 stuff is quite similar and can apply. But in this case, when we get to this level of technology, although some of this function could actually work in an 828, this is really generally reserved for an 840. So once we get to this type of machine technology, we're usually talking about the 840. So what we're going to talk about today would almost be synonymous with the 840. There is plenty of stuff that would apply to an 828, but I'll be honest, I've never been in front of a B-axis multi-spindle lathe that was commissioned with an 828. Traditionally, specific to 840. Now today we are going to look at B-axis and the B-axis specifically. So really it becomes, how do we set up the machine for utilizing a B-axis? How do we manage the tooling? How do we manage dynamic offsets? So as I rotate or change my B-axis around, how does the system calculate that and apply it? So you guys should have a real good understanding of how it works. And if you happen to be lucky enough to be standing in front of one of these technologies with a Sinumerik control, you should be able to start certainly applying toolpath after today. So that would be the big goal for me. Now, I do always like to bring up some reference material because, it's great to listen to me chat for an hour, but let's face it, once we're done talking and you guys have to get out there and make things work, it's always nice to have some additional support material. So if you go to what we refer to as our CIOS website, we love our acronyms here at Siemens, as well as a lot of companies do. So CIOS stands for our support industry. It's actually support industry online. But just go to that support industry Siemens.com website you see there. Usually the easiest way to find some of these documents is just search for the document number. So you see that search for on the far right, that 6FC number. That's going to bring you to our turning operation manual. And this refers to quite a bit of G-code programming and has a whole chapter specific to B-axis. So a lot of the stuff I'm going to show you today is specific to the B-axis. We did get a question to come in. So as far as the questions are concerned, you guys can type them into the Q&A panel or the chat window. If I can, and it's appropriate as we go through, I'll kind of read them and throw them in. But we will do a whole Q&A period at the end as well. So if you want to wait to the end, that's fine. But I do see that Adrian asked, what's the difference between an 840D and an 840D SL? That's a great question. So it really has to do with our drive platform. So we've had the 840 control terminology for quite a few years, probably 25 plus years. So back in the 840D days, that was using our power line drives. So if you've ever been inside of an electrical cabinet and saw the 611U drives with a common power line configuration, but they were a kind of a big, really square white drive box module. Those are power line drives. So whenever you see it just say 840D, then that's going to typically refer to a power line product. The SL that comes in the 840D SL stands for solution line, and those are a newer version of drive module. Those came out, Solution Line, I think we introduced sometime early 2000s. And it's the current drive platform that we sell today. So any current product being sold or all 840D SLs, but that would be the difference between the two. So great question, Adrian. Now, as we continue on, what I will say, the base material, remember I said there's a series of webinars that have kind of been building to this point. Well, the previous one in this series was the G-code programming for Sub-Spindle lathes. And that I go in a lot of detail on how to do part transfers. So I will show a simple part transfer here in this webinar, but I'm not going to spend a lot of time digging into it. If it's something that maybe you missed this webinar and certainly you want to get into more, check out on the Mr. CNC channel, check out that G-code with programming with ProgramGuide for Sub-Spindle lathes. And whenever I refer to ProgramGuide, that is our editor for G-code part programming. That's what ProgramGuide means, as opposed to Shop Turn, which is our conversational programming. So check it out. Like I said, we will do a basic transfer, but I'm not going to go into it in depth, so refer to that webinar for sure. Now, we get into this technology, this B-axis technology from a lathe perspective, and we tend to hear these two terms kind of thrown around in the industry. And generally, we usually hear the term mill turn relate to what we think initially of this base technology. Well, at Siemens, we're a little different because where a lot of controls were limited to handle this type of technology in just their turning engineered control. For us, we said, well, we can add milling to a machine where its base construction is actually a lathe, and that's really the technology we're looking at today, or we can add turning to a machine that was really a milling machine. So since we've been able to support both variants of technology, we actually will refer to a turn mill as a base lathe. So the base technology would be a turning system that has milling capabilities. But if I'm on a 5-axis machine where I happen to have a torque motor in the platter and now I can do turning on that machine, that's what we refer to as a mill turn. So you will hear people talk about a B-axis lathe as a mill turn. In my world or in the Siemens world, we would refer that to a turn mill. Certainly, you could use the terminology, interchange the terminology, but if we want to be a little more accurate, it makes a little more sense to be able to differentiate. Is it a mill that has turning capabilities or a lathe that has milling? From our control standpoint, though, there are some differences because when you commission a turn mill, your base technology is a lathe, as opposed to on a mill turn, your base technology was milling. So the control actually starts up a little differently and it will look a little different. So if you bounce between the two, you know what I'm talking about. We are going to be on a turn mill. Now, the next thing you always want to get your head around, we got a lot of axes going around when you get to this type of technology, and you will get some differences from OEM to OEM, what they like to call things. So I always build a little cheat sheet every time I start working on one of these types of lathes. I want to make sure I know exactly what the axis designation names are. I also got to figure out which spindle is which, right? We all kind of like to do that differently. So in this case, this machine, we have 3 primary linear axes. Those are going to drive the milling spindle around. We have a counter spindle or a sub-spindle. That's going to be our ZS2 axis. We have a B axis that's going to be carried by my 3 linears. And then I do have 3 spindles, my S1, S2, and S3. S1 would be my C axis or my rotary axis main spindle. S2 would be my counter or my sub-spindle positioning axis. And then S3 would be my live tool spindle that's carried by my B axis and by my 3 linear axes. And that is a positionable spindle as well. It needs to be. So as we start to flip that tool upside down or right side up, I need to be able to program that. So if you kind of take a look at the total axis count, we're at what, 3, 5, 8 axes. And I mean, that's not uncommon at all when you get to this type of technology. So how would it look? How does it get commissioned? So it's important to understand where the datums come from when we get to this type of technology and we start to have multiple spindles and we can do handoffs. So the preferred method and certainly our encouraged method when commissioning a machine would be that your main spindle is your primary datum. So all offsets, all movement will basically move relative to that main spindle. So in this case, all travel based off the machine 0 would be a plus direction, including my sub-spindle. So if you look at any offsets, let's say I put the front of the part where that little red bullseye is as my part 0. Maybe that's my G54 or 55, 56. I would expect to see now a positive value get inserted in the offset. And then generally from there, when you get to this type of technology, you want to work from a gauge line. So we're going to get into that a little more, but I expect to see all of my tool offsets be a positive distance from the spindle face or wherever gauge line is on that taper technology to the tip of that tool. But everything's going to back up right off that main spindle. So that's kind of where our primary datum should be. And if you're running into problems, handoff problems, and your machine was not commissioned there, that's probably why you're running into handoff problems. So it's a good thing to try to always commission them building off of that main spindle. Now here is a typical layout of a B-axis lathe. And we certainly see on the right side where you're going to now have a milling spindle that can be spun around. What's important to get your head around at this stage is where is B0? And it's a little different than we're used to thinking. Typically, when we think about angular offsets, 0 degrees is generally always 3 o'clock, right? And then if I want to go to 90, it's 12 o'clock. 180 would be at 9 o'clock, and around we go. Well, generally speaking, most builders, when they commission a B-axis lathe, will set B0 at 9 o'clock. And generally because that's usually the orientation as well for tool change. So when you do get on this B-axis lathe, not only do I have to get my axis designation down, but I got to know where that B datum is, because everything's going to drive for that. All of our tool orientations are going to be based on this location. So, if I got to jog it to position, then that's what I will do right off the get-go. But generally speaking, you should expect B0 would be at 9 o'clock. So B of positive 90 degrees would then swing that tool down to 6 o'clock. Once you get your head kind of around the axis designation, the next step would be, okay, so how do I move this machine around and get it to compensate for the tool length offset, right? So if you can visualize that B-axis head is pointing straight at 9 o'clock, I have some kind of distance from the center of that rotary out to the tooltip. Now, if I swing it down to, let's say, 6 o'clock, well, now my tool is a whole new position. So for me to be able to go to the same point in space on the part, I need to have some kind of compensation. Well, that is all done through a function we call swivel cycle or cycle 800. We're going to get into that quite a bit. But from a jog perspective, you're going to have these beta and gamma fields in your TSM screen. Beta is going to reflect the B axis, gamma is going to reflect the milling spindle axis. And what will happen is cycle 800 immediately gets initiated when you drive a tool around with beta and gamma. So as I rotate the spindle with that beta field, it's going to calculate where the G54 needs to be. So if I set my G54 front center of my part, no matter where I rotate that tool around with this beta or gamma through TSM, it's going to use swivel cycle in the background to dynamically calculate this new location. So I can now move down and get to that same datum point. So that's how you're going to start to work with this technology in a jog kind of orientation. Now, when you start this, really step one would be I got to build a tool, right? I got to build that tool. And then once I have the tool built, I can start to position it around in jog. So for those of us that are familiar with turning in a Sinumerik control, you're used to going and creating a new tool. You get our little favorites library, just like you see there on that left side window where I see roughing tool, finish tool, plunge cutter. Now the first cutter should always represent an OD tool, and the picture should match the tool the way it sits if my B axis is at 9 o'clock or at 0 degrees. So that's going to be your indication of which cutter picture do I choose. So visualize that head, that tool, sitting at B0, and the spindle is sitting at spindle 0, right? So that's your gamma. That should match. How it looks in that machine should match that picture, and that picture should be a tool that can perform an OD turning operation. Now, as we start to move things around with the B, it's going to automatically change which orientation on the fly. So we're going to get there, but this would be step one. How do I build an OD turning tool? Well, if it's a right-handed tool, when I'm sitting at B0, I would choose that first cutting orientation. My tool offsets, they were going to be based off a gauge line. So whether I use a presetter in the machine, I externally set the tool. This is where my positive LF offset comes from gauge line. So cycle 800 will not only manage the internal offset, but it's going to now add this positive length offset of your tool on the fly. So you'll have two offsets on a turning tool. You'll have your Z direction offset. That is our LF field we're referring to there in the picture in the bottom right corner. And then we'll have our WF or our X offset to get out to that cutting edge. When we get to end mills, drills, centric style tools, I don't need that X offset per se, but I still need the Z offset. So that would be, in this case, the I1 projection from gauge line to tip. That's what's going to be inserted. And generally speaking, when I build a round tool like an end mill or a drill, I'm always going to use that first cutting edge that's pointing to 9 o'clock. The only reason why I would use any of the others is if I was putting a right angle head in this type of machine, because maybe I needed to swing around and reach inside a cavity or something along those lines. In that case, then I could use the end mill or the drill that's pointing up or pointing down. But you don't need to worry about, oh, it's going to be working on the sub-spindle, so I have to have one pointing towards 3 o'clock. No, everything's going to be defined at 9 o'clock at 0 degrees, and then cycle 800 is going to handle everything else. So just build it as if it's sitting at B0, and you will be safe. Now, pretty common tool when you get to this technology is what we call a multi-tool. So a multi-tool allows me to have multiple pockets in the spindle for my gamma, right? And then I can position the spindle to different cutting edges. So if your machine happens to be commissioned for multi-tool, you will see multi-tool as an option on the bottom of the list. When you choose it, first thing it asks is for your number of locations, and then it'll propagate however many locations you told it, and you can plug in the degree for orientation for each of those. So usually if commissioned properly, I would expect my first location would be 0, but if for some reason it's not exactly there or you're doing something a little unique, you could put an angular offset in there for number 1. And then certainly if you know that the pockets are all equidistant, like if it's just a 2 pocket, you'd probably have 0 and 180 or some common offset if you needed to offset a little bit for both pockets. And then you can kind of build it from there. And then the way it's going to look in the machine, once created, you're going to see for our pocket location, pocket 10 happens to be the pocket that tool is sitting in, you now have multiple tools built underneath that. So what that's telling you is when I do a tool change to that spindle location, all those tools go with it, but then whichever one I physically called, and I can drive them based on their name, so each one can have a unique name, that's the offset it's going to use. So I would literally have 2, 4, 6, or 3 different offsets associated with this one tool, and then obviously X and Z for each of those, giving us 6 total offsets that I'm managing with that one cutter. Another way you can use multi-tool I thought was pretty cool. I've seen guys use like a face mill, and instead of having the same insert on every pocket of the face mill, they had actually different nose radius inserts in the different pockets. So I could, rough with one insert on that face mill and finish with another one because I had a smaller nose radius, or I changed maybe the insert grade. It's another way I could have a face mill that's got, 6 or 8 inserts, and I could use that for turning of steel and aluminum and Inconel just by having different grades and different geometries of inserts in each pocket. So you can get pretty creative with this multi-tool scenario. Now, when it comes to building your offsets, we got a question comes in. And one of the tools on the tool is offset in Y. How would you input that into the machine? So there would be a Y field. You can't see that here. And that is part of commissioning. So your machine may not always have a Y offset, but it can absolutely be added. When we get over to Sinutrain, we can take a look at that in a little more detail. But you can actually add in an additional Y component to the specific tool. You know, you always get that Y offset in the work coordinate like we're seeing here, but we can have a Y offset in the tool as well, in the tool definition. So when it comes to setting your work offsets, generally I always like to have two offsets. One work offset's going to drive and sit on my main spindle. The other work offset's going to be sitting on my counter spindle. Main's going to be pretty straightforward, right? So in this case, I'm not doing anything too fancy as far as I'm not doing like eccentric turning or anything. So everything's going to be working in the center line. So I'm not worried about plugging in any kind of offsets in my X or Y per se. But what I am going to do is I'm going to have a Z offset in play. So remember from that earlier picture we looked at, that's going to be that distance from the spindle face or machine 0 out to the end of my part. So there's my positive. And when I get to my secondary or my counter spindle offset, the big trick here is you want to make sure you click on the details field for, in this case, G55, and you want to use the mirror function. So once I check and I'll put a little checkbox there, I see it in this lower corner. Once I have a checkbox in the Z for the mirroring field, now it'll automatically invert my tool motion. So all of my Z's engaging in a part will always be negative. So if I'm on the main spindle and I give it a Z negative, it's going to go towards the main spindle. So the machine's going to move to the left. If I'm on the counter spindle and I give it a Z negative, the machine's going to actually move towards the right. What's nice from a programming standpoint is, one, if I have common tool paths that I want to implement on both my main and my sub, they'll automatically transfer without any reprogramming. From an operator or programmer perspective, I don't have to keep thinking about which spindle I'm on. I can kind of always keep that rule in place where I move negative, I'm cutting. I move positive, I'm going in a clearance direction, no matter which spindle I'm on. So I'm a big advocate of using the mirror function for my counter or my sub-spindle work offset. And then the way that the work offset handle all of it instead of trying to mirror in the midst of the program and all that stuff. Now, if you watch the shop turn transfer program webinar or B-axis program webinar, I was using this chuck data or spindle chuck data area quite a bit. When you get to G-code, it really doesn't have much bearing at all. What it does do is it does set up the graphics during simulation mode. So if you want to see the chuck jaw projection kind of look like your machine does, by all means plug it here, but it's not going to have any bearing on your program motion. So it's really just used for simulation, and really only simulation when I'm just looking at from an editor perspective or simple 2D simulation. When I get to, you're going to see some machine space simulation, that's using STL files to represent the chuck. So this is limited use when you get to this type of programming method. But I usually still will define it and make it match my chuck jaw, my chuck projection. This way, things in simulation look pretty close to what I'm setting up. Okay, so we're in. We defined a tool. We're gonna set it. So in this case, you're gonna then come down. As long as I drive my B axis with my beta field, and I drive my spindle axis with my gamma field, I can then put the tool in any orientation, do a tool set, and it will calculate the appropriate value for both my X and my Z. So, you know, even though I might have set and built that OD turning tool at a B0, maybe I wanted to just do a quick scratch on my part, right? I want to turn a little bit on the diameter and check it. I can swing the B down, I can flick the spindle over, take a cut, do my set X, type in my diameter, and then it's going to know that position. So if I swing it back up and I go back to 0, it's going to track all that. You got to make sure that you're using the beta and the gamma to move it around, because once you move the rotary with an actual direct axis command, like G0B 90, there's no tracking in play. It has to be done with the swivel cycle. But what's happening is that's automatically inducing our swivel cycle in the background for you without you having to go to a swivel event and try to turn it on. Now, when you get to Z, certainly I could set off my part. I could set off of a datum on the main chuck or a datum on the sub-spindle. But again, you always want to make sure you're driving that tool around with your beta and your gamma. So this way it's going to know what it has to compensate when you do the set. If you're going to a presetter, it's a little different scenario, and generally that gets handled automatically, but you would still drive the tool with beta and gamma if you're going to use, like our standard touch presetter cycles for sure. Okay, so why do we need cycle 800? I've talked about it quite a bit. Referenced, what is it truly doing? Well, it's doing the math on the fly to not only manage the tool projection, but to manage what we refer to as our join offset. So that is that I2 value you see here. So as I swing that tool around, I have to take these numbers into account. Now, if I push this off on the cam system, which you can do, the problem now comes in if anything changes, if there's a discrepancy in my physical machine offset, or there's a change out on the floor of my tool projection, now I have to repost the entire program. You use cycle 800, and now the cam system just drives everything from the insert tip location, and you let the control manage everything. The only thing you really have to watch as you swing it around a little bit is that you have enough clearance to swing down and then approach the part. That gets a little tricky sometimes when you start to move that B axis around. Now, what'll happen here, and this I want to spend quite a bit of time on because it does tend to mess people up a little bit. But in the control, what we do is we will automatically change the orientation position of the tool based on where she lies in the degrees that it's programmed at by the beta and gamma. So, I said originally we were doing setting that tool up when it was sitting at 90, it was going to be a cutting edge position number 3. That would be the cutting edge associated with that OD tool picture that I picked. Well, if I take that tool and swing it so it's completely vertical, so I'm down at 6 o'clock, it no longer is treated as a cutting edge position 3. It's going to be treated as a cutting edge position 8, and it's going to center the Z axis on the insert. If I swing it down and I'm at 0, it's now going to be thought to be a position 7. And the system automatically does this. So if you start working with CAD/CAM systems, this has to be known by the CAD/CAM system. If the CAD/CAM system doesn't know how to calculate the transition point at when this changes, your posted programs aren't going to work properly at all. Now, there are some other solutions there, and I'm going to show you, but I want to get everybody's head around this. So we're going to look at this in the control in 2 different scenarios. First, we're going to look at it with a VNMG, and we have a VNMG, and then we're going to look at it with a VNMG. After this, we'll come back and we'll actually look at with a round insert, because that's also pretty popular when getting to this type of technology. So what I'm doing here is I'm switching over to Sinutrain. For those of you that have been on a lot of my events, you're used to seeing this. If you haven't had the option or the privilege, Sinutrain is an offline programming package that allows us to basically create a duplicate of your machine tool here on a PC. So we were talking about different tools, right? So first things first, maybe I'm using a standard, we'll do, where's my DNMG neutral tool? So I'm going to do a quick tool change, do it through TSM. I'm going to do a quick tool change to that tool. So at B0, you see how my cutter orientation was set up in that position 7 like we just showed. Now, I don't happen to have a swivel carrier running right now. So that would probably be because it was canceled maybe through a part program. So you don't have to worry about that. Normally if you're a mill guy, you're looking for the swivel button that doesn't exist on the lathes, because all you have to do is just give it, and it can be a redundant command like a B0, and that'll turn on my carrier. So now I always want to make sure that this carrier is running, because this is what tells me it's tracking that offset. So now watch the tool definition, the tool description. So let's say I position the B axis through the beta. I'm not doing it as a direct move because then I won't get compensation. All right, so I'm going to do beta here. And I got swinger to 45. Look, it just changed the tool orientation. So no longer is it centering the insert on the center line of X. It's now, if I position to 0, going to be at 2 tangent points. And if I swing this all the way to 90 degrees, watch, changes the orientation again. So how does this all work? So let's take a look. I created a simple little part program that we can explore on our DNMG. And what we're going to do is we're going to first take a quick look at this in simulation, but then I'm going to show you a machine space model driving it around because I think it becomes even a little more clear when you see the machine motion. So first things first, the system came down, positioned to B0. So if I look at my insert, it's dead center on my x-axis. Now I back off. I'm going to do an orientation change, and I'm going to 62.5 degrees. And that's an important number, so kind of remember that one for a little while. But if you look, let me zoom right in, you see that now the tool is now being tracked as an OD tool, so my cutting edge is now going to be tangent to the center line of X and tangent to the Z. And as long as I stay within, so now I'm at 45, or I go to 27.5, as long as I stay within this axis range, it's going to be treated as a cutting position number 3. The minute I go beyond that, so in this case, I went from 27 to 20, or 27.5 to 27 degrees. Look, it just jumped over. Now I'm back to centering on the insert. If I go back to my 0, now I'm going to stay at the cutting edge 7. So how did that work? Why did that do that? Well, what's the geometry of a DNMG? 55 degrees, right? Well, what is half of 55? 27.5. So we know, based on knowing that it's a 55-degree insert, you told me that when you defined the tool, or hopefully you did, we can then say, okay, so as long as I see a B-axis move, that's going to stay within that range, so I know the insert would be vertical and it's not going to go beyond, then I can treat it as a cutting edge position 3. If I go less than half of the included angle of the insert, then I'm going to have to switch over to a cutting edge position 7. If I go greater than, so now we're going to get to show you some cool stuff. I'm going to use a machine space model to run the same program. But if I go greater than, then I'm going to, so here we go, neutral, then I'm going to transfer over. So when your post is trying to figure that, that's the trick, right? You take the insert, divide it by 2, and then as long as I'm within that number, so there I'm at my 62.5 degrees, or my, come back down, here's my 45, you see how it's tracking, staying in the middle there, or I come down to my 27.5 degrees, as long as I stay within that range, I'm going to stay as a cutting edge position 3. I go over just slightly, and then I'm going to, in this case, go to 27. I'm now going to turn over to be a cutting edge position 7, and now I'm centered on the insert. Because if you think, now it's leaning down. I could never actually touch this OD with that orientation because my cutting edge tip, there'd be a gap, but the further in I go on the insert, it's now touching. So that's how it starts to calculate. And it is going to be dependent, certainly on the, so I'm going to shut this off for a sec, on the insert geometry. Oh, oops, picking the wrong axis. So if I go and take a look at our VNMG program, I got one right here. So this is going to be a 35-degree insert. So now if I look at it, and we can go right to our fancy simulation and run it. Now it's taking, again, half of that angle. So there I'm in a cutting edge position 7. But now, since I have more room, because it's only a 35-degree insert, now I can go all the way up to 72.5. All right, or I can go all the way down. Well, first I'll do my 45. Then we're going to come down to 17.5. So again, 35 divided by 2 is 17.5. So 0 plus gets me to 17.5, or 90 minus gets me to my other angle. And that's the range I can be within on this tool. And the minute I go on either side of those numbers, greater than or less than that total angle swing, then it's going to switch to the next cutting edge position. Okay. Now, I did mention, and we can stop that, it's good enough, that it's pretty common to also use button style tools, right? These round tools are real popular. So when we got to the round tool, because there wasn't any clear point of transition, right? With a diamond tool, it was pretty simple. You know, once that insert, the side cutting edge of that insert went beyond vertical or horizontal, then there's our transition point. That's when we flip over. When I get to a button tool, well, when do I make that decision? So all we did was we treated it as 45. So we were thinking of a button tool like if it was a 45-degree insert. So as long as you stay within 22.5 on either side of that 45, then you're going to stay in that cutting edge position 3. But if I go less than 22.5, or if I go greater than, what am I, 90, 80, 70, 65.5, right? I go greater than, then it's going to switch over to centering that insert. So I do have a little example of that. We'll jump on back. What are you doing? There we go. Being a little lazy. This is the beauty of running lots of windows. Let's see if she's going to come back on me. I got the wonderful Windows thinking scenario. All right, just give her a second. If not, we'll move on. But I want to show you the button tool, because there's two different ways to set up or configure the button tool. I can configure it working off the leading edge, or I can work off the center of the insert. So that is always a question that we get posed by the CAD/CAM guys, that, you know, if they can't understand this tracking mechanism, how do they get the system to work maybe off the center of the insert, and let them at least compensate for the radius. So here we have a round tool. So if you looked at it in graphics, it would be kind of hard to tell as far as where the insert orientation or the holder is. But in this case, at a B0, looks like I am, let me reset this, getting ahead of myself. First, I want to look at it from a normal definition. So if we looked at this tool, all right, there's my RCMT, I called it. You notice that when I define the tool, I'm using the orientation where my insert is going to be touching this edge. That's that little indicator. Hopefully you guys can see it. I know it's a little hard to see. So there's two ways to define it. I can do that, or I can define it like button tool number 9. That's your cutting edge 9, all the way over here, the farthest to the right. On all of these, you'll see there's a cutting edge 9. Your machine does have to be set up or commissioned for cutting edge 9 support. But once you have cutting edge 9, then it'll work from the middle of the insert. So sometimes with the CAM systems, if they have a hard time understanding this functionality within our control, we end up being forced to go to that cutting edge number 9. So back to the round. And again, I am intentionally spending a lot of time on this, because this always stumbles guys up when they're trying to work through their post, is how is cycle 800 compensating? So there you see we're touching that insert point, but I'm dead center on the X. All right, pull off. There, I'm now somewhere within, so I did a B of 45. Now, if I go to a B90, you see how now I'm shifting in. So obviously, if this was a real part, that would be bad. But you see now I'm working off the center because I positioned it to a B90. If I stay within that 45, that 22.5 degrees, so half of 45 on either side, she will stay in cutting edge position 3. But once I go beyond it, it's now going to, so I went from 67.5 to 68 degrees. It's now going to shift off, and I'm now overcutting or undercutting because I wasn't anticipating that. So if we look at it, we should be able to see it here real quick. Come on down. There you go. So here we're centered. Oops, I'm gonna Try to center this a little bit better for you. Okay, so there we're centered and touching. And we come over. Now I'm at a 45. And as I change the orientation, there's your 90. So now we're centered there. Certainly would be bad way to cut. And if we stay within that 22.5 degree range, I'm going to stay at a cutting edge position 3. But once you go over, boom, I'm working now. I'm centering in that next axis. So if you need to handle this as a working off the center as a cutting edge position 9, you build the insert as a position 9. And then what will happen is no matter where we position it, it's going to maintain that center point. So here, if I call up that cutting edge and we run it, you're going to notice no matter where I position the head, it's always going to work off the middle. So now it's up to my tool path to then shift or compensate for the radius of the tool. So the only downfall here potentially could be that if I have an insert issue, I got to make sure I have cutter comp there too, where I can do like a cutter comp wear strategy or something, or I would have to repost for any issues there, because I would be letting the cam system now compensate for the radius. And my tool offset would work from the center to gauge line. So wherever we put it now, we're working from the middle of that tool, the middle of that radius. So that's that cutting edge position 9. And we should be good. Okay, so hopefully that maybe clarifies a little bit of how this works. If you're users of this type of technology, that may have stumbled you, certainly in the past. We're now going to take a look at our part program example. So for time's sake, I'm not going to write this program from scratch, but I do want to go through and highlight some key points in the program and how your toolpath could be supporting. So we're going to do some basic turning, but we'll start flipping the tool around. We're going to do some simple milling. We're going to do some milling on the face, milling on a flat on the OD. We'll do some inclined milling and drilling by the time we get done with this. So there's a lot of operations. It is pre-programmed. So if I come over here, I do want to give you guys a kind of a once-over teaser of what this toolpath's going to look like, and then we'll dissect it a bit. So if we look at it, and I'm going to zoom back. All right. Oops, missed my cycle start. So first I'm going to start, and I'm going to do a basic OD op. Oops. Oh. Okay, so I had left a command in place for later when we want to skip over our main spindle ops, but I forgot to suppress that. So here we go again. So we're going to come in, we're going to do some basic OD turning. Now, first thing I'm going to do is I'm going to do some simple OD turning. That tool was defined in cutting edge position 3 when I'm at B0. And then I'm going to say, well, what if I want to face the front, but I want to bring the B down at 90. So there I used a beta and a gamma switch. Now we're going to come in, we're going to do some basic milling off the face. Once we do some simple face milling, I'll kick up my speed a little bit. Then we're going to come off the side, do some planar milling, positioning our axes. We'll do a little drilling on those planes. So, by the time we get to the end of this, now, yeah, from a toolpath side, I had, of course, I have an M30 staged here. I had, just used CAN cycles. If you're posting from a G-code, just visualize that we're going to have a G-code program in place of the CAN cycles that I happen to be using. For me, it was just easier to use CAN cycles for the toolpath. But the positioning and the placement of the swivel cycles and how all this works, that's really would be the same if I was coming out of a CAM system or I was doing it through G-code on the control. So we are going to do a part transfer. This is where I was saying I'm not going to spend a lot of time describing it. Check out that webinar, but there we're going to grab it and jump over to a part transfer. Then we'll flip over to a neutral tool, do some different orientation changes while turning. We're going to do a little bit of milling on a compound angle and some drilling on a compound angle. So this should really start to get you down the world of working with B-axis technology when we're all said and done. So let's take it kind of a piece at a time, kind of chunk it out. I'm going to show you a few little tricks that I do and hopefully kind of help you in this technology range. So first things first, we're going to go in, we would start writing our program, and we're going to talk about our program header. Your safety line, pretty typical, you know, I usually start with a G18 because a lot of times we're going to turn first. Obviously, when we get to milling, we're going to be a G17. I'm going to be in absolute positioning, not incremental. So there's my G90, whichever work coordinate I'm using. So in this job, I actually use 56 and 57, 57 being my mirrored offset for my sub. Wanted to be in metric, so I want to use my G710 command, or 700 for inch. Those of you guys that have been on events with me in the past know I'm a big advocate of our 3-place unit of measure. So if you guys don't know it, hey, check out another webinar and I'll tell you exactly why. Figured I would set up G95, you know, that could be done later. Now it is important that I potentially want to cancel cycle 800 because on these lathes it's pretty much active all the time. But before we get to a SUPA command, you want to be careful when you're pre-positioning the axes around. Cycle 800 or SUPA won't suppress cycle 800. So if I'm going right to travel limits, I could get an over travel. So it's usually a good habit to get into. In this case, I usually will cancel cycle 800 right from the get-go. I set up my work piece, and then we get into defining which is going to be our main spindle. Now, I like to use the group commands when I start programming this, and certainly you can have your CAD/CAM systems output the group commands. It becomes really handy to manage large chunks of code, to be able to copy chunks of code quickly, because everything in the group will kind of follow with the group. So from the control side, groups are really easy to build. You just under edit, you hit build group, you give it a name, and you got a group, and then you can expand and contract these. So you'll see that when I get to the live section. From a CAD/CAM posting program scenario, you want to put in these group begin and group end commands. Now the groups will become very important once we get to multi-channel lathes. So upper turret, lower turret, that's how we direct where our toolpath is going to be to move our upper and lower turrets around. As long as I have a single path, really I don't need any of those extra variables other than what's in the quotes. So that would be the name of my group. So it could be something as simple as just group underscore begin, parentheses, and you'll always put a 0, comma, some new name. I usually will put the operation or what's happening in the name. And then the 2 comma zeros is fine for this technology. And then when I want to end the group, I just do group end, group underscore end, open close parenthesis with the 2 zeros. That's enough to then when you get to the editor in our control, you'll get the group's functionality and you can expand and contract all of those. So from there, when it comes to working with your workpiece blank, if you haven't been on a multi-spindle lathe before, you do get the option of picking either the main spindle or the counter spindle. So we can work in either direction or on either side first. We could transfer from the main to the sub or the sub to the main. You don't even ever have to transfer, right? So if you happen to be lucky enough with one of these machines and maybe you're doing a simple job on the main spindle and you want to use the sub spindle for a different job, you could absolutely do that. And then you would just set up the blank to work off the counter spindle, and then it would work like if it was a standard single spindle lathe. And then you get to the tool change. So the tool change becomes pretty important. Obviously, we want to make sure we set up now the diameter mode. You want to be cognizant of diameter mode because it will affect your SUPA positioning. A lot of people don't realize that. So diameter mode off or on is basically whichever axis is designated as my diametric axis. In this case, it would be X. Typically, it would always almost be X. Then if I have it in an on state, all X values are going to be treated as diametric values. So the axis will go half that distance. If I have it in a diameter off command, then it would go that full distance, right? It would be treated as any linear axis. From there, I'm going to make sure that cycling 100 is canceled. I know I had it previously, but when you're looking at blocks of tool change, usually it's pretty common to plug it in over here. Tell it where you want to go. Now, SUPA is a non-modal command, meaning it's only going to work for this one line. So if I'm doing a couple moves and I break them up, like I have here in this case, I wanted to get my counter spindle to a safe location. So there's my SUPA line, and then I want to drive my my X and Y and Z and B to a known position, probably for tool change or certainly for clearance before I get into swiveling. Then you can load your tool. We support both, obviously, the name tools or tool numbers. But when you get to this technology, the tool number has to be in the name. So if you're familiar with turning, you might be used to, T3 is the turret location number. You don't have a turret here. So it is not the pocket location, because this could be a random tool changer for all we know. Not usually, but it can be. So this is going to be set up much more like a regular milling machine would. So I would need the name to be named a number. So we can look at that here in a second. And then you want to set up your primary main spindle. So that's what the set ms command does. It's basically telling the control which is going to be my main cutting spindle at that point. And it's also how my S commands get mapped. So this is a case where a lot of people always think that you have to have the S1 equals or the M1 equals or the S2. That's what handles driving my spindle commands. Well, the set main spindle command will actually handle that as well. That was really what its primary purpose was for. So if you take a look here, let's say for argument's sake, I want to fire up spindle 1. So I can absolutely tell it, and I'm going to be in caps, set ms number 1, and yes, I can say spindle 1 equals some RPM. M code for spindle 1 will equal a 3 for clockwise. So this would fire up the spindle at, and of course my override is low, get it to 100%, so 1000 RPM. Now, since I had the set main spindle command, I don't actually need the M1 equals the M3, M1 equals 3. That maps the S codes and the M codes to that spindle. So if I start to then just change which my set main spindle is, see now number 1's not running anymore, number 2 is. So you can kind of go either way. The tricky part, and usually why I don't have posts do this, is now it's asking for a little bit of logic for the post. And what happens is, so now number 3 is there. So let's say for argument's sake, I wanted my main spindle to turn on, but I was also going to have a tool spinning because maybe I was going to run an end mill while I spun the C axis. So the minute you need to have 2 spindles running simultaneously is where we would need the S3, maybe I'll do 1500 just to do something different, and the M code for spindle 3 equals 3, where I would need to use those. So now I'm actually turning multiple spindles on at the same time. So from a post side, typically I will just adopt the S1 equals and the M1 equals, but with the set main, you don't actually need it. So if we look at our program, to just start to go through the beginning, so here's where you start to see the groups come in play. And what I do is they allow me to expand and contract large chunks of code, so I can look at almost the entire part program in one overview, which is real nice when moving around in these types of programs. Plus, if I wanted to reuse the toolpath that's in this group, I can copy the group and paste it somewhere else, and all the toolpath comes with it. There could be 1,000 lines in here. It'll transfer with it. Now, when you're working with groups, to create them, you just need to be down somewhere on a blank line, and on the edit button, you hit build group, give it a name, say accept, and now you get a group that can be expanded or contracted. Expand it, hit enter, you can start typing your code. You can compress it, right? So that's how you build them. Obviously, you saw the syntax for how to build it from a CAD/CAM package. Now, another thing that's kind of neat, when you're working with programs with groups, if you expand your vertical keys and go to the view option, you can expand or contract all of the groups at the same time. So this is kind of handy. So I can, I can look at chunks of code and I close them. And so it's just, it really makes just moving around a part program a little bit easier. So we see our safety line, cycle 800. This can be driven via the various function. And I could use swivel tool or swivel plane at this point, because either way, I'm just going to pick a 0. Or you can just type cycle 800 open close parenthesis. That will also designate a cancellation of cycle 800. Workpiece blank. Now I'm going to set up my blank on the main, but you would pick main or sub-spindle or counter spindle, and then just describe it like you always would. My tool change. So here I do have a diameter mode on command because I'm going to be turning. So I do want to be cognizant of that when I get to my X command, because it's not going to machine 750. It's actually going to do that as a diametric. So I'll get half that move. So you do want to be careful. I did mention the tool call. So this tool, CNMG 432, if I go into it, is now sitting in pocket location 1. Well, this is more of a traditional carousel or machining center style tool changer on these machines. So I can't do a T1. That it'll come in and say tool not available. I don't understand what you're looking for. If you want to drive based on numbers on this type of machine, then I need to name the number. Where on a regular turret lathe, I can drive it based on the turret location. So that's just a little difference that I want you guys to make sure you're aware of. Map your spindle, fire her up, and we're ready to turn something. So if we go take a look at the next step in the program, next thing would be getting into using swivel cycle. So there are 2 different cycle 800 functions. We have the orientation of a plane, and that's going to be used if you're milling or drilling. When you're establishing a plane, but you also want your coordinate system to be aligned to the tool. So G17 would point in the direction of the tool. So now I can use all my can cycles, all my drilling can cycles, and it'll work in any plane orientation. But if I'm using it for tool orientation, for like a turning tool, there's a hybrid version or a secondary version of cycle 800, and that's called our orient tool. So this is what we're going to look at first, and this is real popular on a B-axis lathe because you want to be able to flip the tool around and do all this stuff. So I come in, I want to drive my tool, so I'm using the align tool turning tool function, and that could be posted through my cycle 800. Now there are these different carrier names, so we want to talk about that because it does get a little more complicated than like we're used to in a mill. Milling machines generally only have 1 tool carrier. That's what the TC stands for driving a swivel cycle around. When you get to these lathes, you get quite a few more. But I would then just tell it where I want my B to be pointing. So I'm going to use a B0 and a Y0 or a gamma 0. And then when I go down to do my next orientation, as you saw quickly when I did the first overview, I wanted to swing down to 90, and I knew I had to spin my spindle. So generally with the spindle, you're only ever going to do 0 or 180, right? I'm only flipping it 180 over, and the only time you would have anything other than that would be if you were using like a multi-tool, but the multi-tool is going to handle that. So you're still using 0 or 180 because the multi-tool knows enough to say, well, 0 for that tool isn't actually 0. It's at my 90-degree orientation or however many cutting edges I had. Now the one thing that the system will not know, because you're in G code, is if you have the spindle running the right direction. So that is totally on you. So if you get your M3s and M4s mixed up, it will try to run. Shop turn handles all that. So there's things that shop turn knows that we don't know in G code. So you do have to watch. And in this case, originally in the previous, go back one more, I was running in an M3 for my OD op, right? Now I'm going to have to flip to M4 because I inverted the cutting edge around. So now my spindle has to run the right direction. So in that case, then I just have my basic tool path. Now, when you start working with cycle 800, especially from a CAD/CAM scenario, you're going to need to know what all these little commas mean. At the control, you don't care, right? Because at the control, I'm going to open what we call a data mask. That's this little conversational page. It's going to fill out this string. you should never have to edit anything in any of our strings because we have this kind of hybrid conversational and G-code mix. But if I'm writing a post, I need to know, what is this third variable over? What does this fourth variable mean? Because the post is going to fill all that out. So if you go back to that COS website that I showed you earlier, and you do a search for our job planning manual, so again, use this document number to get there. This manual is a great manual. It's got all kinds of tons of great information. But the big one you're looking for is in chapter 20, programming cycles externally. And that's not only going to show you the full breakdown of cycle 800, but it's going to show you all our CAN cycles. So, you know, if you're figuring out how do I post to a drilling cycle and I want to know what all these variables are, it tells you exactly what's the third variable, what's the fourth variable. So this is the Bible when we're working on posts and we're trying to get posts to output our cycles. Is you want to go to this. So download this manual for sure. If you have any trouble finding any of these manuals, send me over an email. Certainly I will dig into it more for you. Now, I'm showing you how to manage the tool orientation through cycle 800. Other OEMs are going to do different things. I can't say if every OEM out there is supporting cycle 800. Most of the big ones that I know of absolutely are, but I did want to give you an example of how maybe another OEM would do it. So I work quite a bit with DMG. DMG makes a very well equipped B-axis lathe, their CTX series. I get a chance to get on quite a bit, a very impressive machine. Well, the way DMG does it is they use this TC command. So that's actually in place of my M6. So I guess I kind of overlook that. You guys aren't used to having to command a tool change in a typical lathe. You know, usually you just give it the T code, right? When you get to these B-axis lathes, it's pretty common that you do have to program a tool change command. And in the DMG, that's what this TC command does. So the TC command was going to give you a cycle string, and here you're going to kind of drive the beta and the gamma a little bit. Where there's a difference here to our cycle 800 is this is only setting up the calculation for where it's going to have to move G54, so I get to the same 0 point. But you're still required to actually position the B and the B axis and the spindle axis to these locations. So even though you did a TC command, if you don't physically drive with a rapid B and a rapid C or whatever the spindle designation is, then it's going to be running totally wrong positions. For us, doing it through cycle 800, it not only makes the calculation for you, but it also moves the axes to that. So it really combines two functions in one. But what I would say here is, you know, this is pretty high technology machines. I would defer to the OEM. If DMG is saying, no, there's lots of other reasons why we want you driving everything with the TC command as opposed to our direct cycle 800, I will defer to them. The irony in all this is they're issuing cycle 800 in the background anyway, so you're still going to get all those advances. But in general, a lot of cases, as long as they have cycle 800 commission, you don't have to do all this TC stuff. You can drive it with our swivel cycle. So there's definitely pieces of the puzzle you're going to want to talk to the OEM about and see if they support it. You know, WFL is going to do something a little different. Index is going to do something a little different. Doosan might do something a little different. So certainly talk to them. What I'm showing you is certainly a very universal scenario. So if we jump back to the program real quick, just to kind of show you. So here we have the turning operation. We can just do a quick little M30 there. And here you'll see I have my cycle 800. Now, you do get multiple carrier names. This is something you have to pay attention on and you have to be aware of. So why is there head 1, head 2, or maybe I go to my plane and all of a sudden I see mixed 1, mixed 2. So what that is doing, and what I have to get my own mind around, is for an aligned tool, I'm going to have a carrier for my main spindle and my counter spindle. And for a line plane, I'm going to have a different carrier type, one for the main, one for the sub. So you actually have 4 different carriers in this type of machine. And then if you have Traore commissioned, then you potentially could have another 2 transformations for the main spindle and another 2 transformations for Traore for the sub-spindle. But we will leave Traore and TCP functionality for another webinar for sure, because that gets a little more complicated. But you just want to know, and this naming is going to change. It's totally dependent on the OEM what they want to call. So not only do you want to know what the preferred method of driving the tool orientation is, but you need to know if you're using swivel cycle or cycle 800. It's the same term, same function. You want to know which name is associated with which spindle and which function. So that's one of those things I put on my little cheat sheet, right? Not only do I know all my X designations and my travel limits, but I know, okay, align tool is using head 1 for the main, head 2 for the counter. Align plane is using mixed 1 for the main, mixed 2 for the counter, and you'll see we'll select each of those. But then it's just a matter of giving it your beta and your gamma. So I know you set your 0 with it at B, but keep in mind this cycle is also taking into account that joint offset. So even though I'm not moving the B, I still need to issue a swivel cycle or a cycle 800 to do my compensation so everything positions properly. So as I simulate, it's going to know that, that I'm compensating for those joint offsets. Now, you don't see the holder in Sinutrain simulation or base editor simulation, but one of the things I want you to pay attention of if you're using this is we give you the insert screw. So if you look, you see the little dot there in the center of the insert, and then as I flip it over, that's an indication to you what orientation the gamma is in. So that's a real great trick to know, because other than that, you don't have a lot of ways to kind of conceptualize the orientation of that spindle. So that's just a kind of cool trick there. And then away we go, right? Now we can start flipping that cutter. Now you do have to be careful. So if you put the orientation angle in a scenario where the cycle doesn't think that it's appropriate for that cutting edge direction, our cycles will still do some error checks to tell you that you have the wrong tool orientation selected. Certainly if it's straight G-code, there's no trapping at that point. It doesn't know. So it would run, and potentially if it was going to, it could overcut or undercut. So we roll around, we start to manipulate with our orientation tool. Now I'm going to do a basic tool change. So the tool change stuff is really the same as we talked about before. The big thing is I might want to add, I'm going to have to add my mapping of my M codes and probably switch my set main spindle to my milling spindle. So this would be my third or my live tool spindle. So we plug in that tool into the machine. Now, when I get to the actual operation, one of the tricks you're going to need to remember is you will have to change your plane. So I'm in G18 when I'm turning, but I'm going to be in a G17 when I'm milling. And whether I'm milling on the face, like this little trichoidal tool path, or I'm milling on the outside peripheral, I'm always in G17 because the swivel cycle, that's what's going to handle the shifting. So what is swivel doing at this point when I'm using an aligned plane as opposed to the aligned tool orientation? Well, now I can start to move my 0 around. So here I'm going to come back and just drop right down. So if you watch this little animated diagram, I'm using between different segments of the swivel plane, I can move my 0 around, and then I can rotate my coordinate system around to get into my right orientation plane. So for the first example, it's pretty straightforward. Oops, got one too fast. So first one, I'm going to drop my coordinate system on the front center of my part. So here I really leave everything at 0. I just want to make sure I call this cycle up. So now it knows that it's working from the face. It's establishing the Z plane from this orientation. Then when I do my milling cycle, I can use my little slotting cycle, or I can have some just basic G-code toolpath to mill based on that face orientation. When I go to do an interim orientation change, now this is where I want to start to be careful. Keep in mind my tool's down by my part. So I can do a SUPA command to get me to a safe spot. If you're going to leave swivel cycle active while doing the SUPA, don't try to shove SUPA all the way to the extent of its travel. Or what you're going to see is we can play around with the retract command as long as your machine's been commissioned for it. This is a nice way to handle how it's retracting in different strategies. So if you look at the part program, and we're going to go get rid of our M30 here. So there's my tool change, grab my cutter, my end mill, do my M6, set my main spindle for my milling. We want to make sure I have a G17. Now the G17 could also be done right here in the swivel cycle. So kind of 6 of one, half dozen of the other. Now right now I have a no retract. So that means wherever she was sitting, it's going to move. It's going to physically move to maybe that one or go over to this one, right? So I can do, here we'll first take a look at it with no retracts, because you want to be careful as you start to move it around. And I'm a big advocate for using the retract within swivel, because it's independent of what's active. It doesn't care if diameter mode's on or off. It's always going to that known defined position. So here we'll just do a quick little run up to this point. So we're going to see some milling. All right, good. So we're turning. I'm going to slow her down a little bit now. All right, so we face it off. She goes, returns, grabs the tool. So you see now I am oriented. We can maybe do a little rotate for you guys. And now we're flipping. So you see this dive right here? So that would have been because if I watched where it's going between my tool changes, or between my orientation change, let me start it over again. So there's my first one, right? Okay, now we're going to slow down. So she's not going very high on the slide, you see, because in this case, my SUPA, so I am like right on that edge. I could have been below center line when I approached that. So you want to be careful there. So if I use a retract strategy inside the cycle, then I can have the machine drive to a predefined location. So there's multiple strategy scenarios. You are going to be dependent on how the OEM commissioned the machine. The one I like to use on this technology is either a ZXY or an incremental. So if I have my tool pointed at like a 45-degree angle and I just want to go straight back, maybe change it from 45 to 60 degrees and then come back in, I don't want to go all the way back to some safety location. So I might do an incremental and then give it my direct distance based on the orientation of the tool. Or I can do a ZXY. This would be a predetermined location. So now if you watch, and we take a look from a side view real fast. Oops. There you go. A little jerky for you guys, but so watch after we do this next orientation. So you're going to see the head's going to go way high because that was the predetermined location. It's also going to do a straight Z back. And there I didn't do any, so it was really close when it did the retract between the two. So that might be a good one for an incremental, just to get back just a little bit more, because there's no point in swinging all the way back into space if I'm just orienting the part around, but I might not want to be too close. So those are some things you can start to kind of pay attention or play around with when you're kind of using this swivel cycle for orienting this technology around. Okay, so we come in, drilling's really a lot of the same as what you saw with milling. So we're going to have our tool path. We're going to use a swivel plane to orient to our different planes. In this case, it was really copy and paste of the swivel planes because I'm drilling on the same planes I was milling. And then you can just go in, do your normal M call to drill. So I'm not going to worry about breaking into this. I think you guys probably get the gist of drilling, but basically M-call sets up your modal call, right? And then any positions I want to drill. Now, when it comes to my Transfer, my part transfer, again, refer to that previous webinar. But here, this is a straight G-code transfer. So the big thing that usually changes, you want to make sure that your M codes for opening chuck while spinning or not spinning. And there's a bunch of different scenarios for chuck opens and closes, whether we're using coupling on or off. This was a very simple static transfer. What is kind of cool, and I did talk about it in that webinar, is the workpiece set focus. This has no bearing other than in simulation. I can change. So if you watch, the system automatically changes the view once it transfers to the next spindle. So I do that with this workpiece set focus command. So this is great from a simulation perspective, has no bearing on your part toolpath at all. And then we're going to go grab a neutral tool. So here I can jump in, we can grab a neutral tool and change some orientation angles, and we can fool around with that. So we're now going to set our main spindle to the counter spindle. That's going to drive the counter spindle as my main spindle. And we can play around with those different orientation scenarios. So if we look at it, boom, jump back in. Okay. So we're now down to the part transfer area, right? So we drilled our holes. So I establish a plane, establish the next plane. One of the tricks you can do with building the planes is do a final rotation about your Z. So you make sure that your X and Y are pointing the same direction. So this way, if you're using common position toolpaths, it's the exact same toolpath to handle both the geometries as well, whether I'm milling or turning. So that's pretty common inside a swivel cycle. You might see this final Z of 180 or whatever direction, and that's just clocking which direction X plus and Y plus are in. So I like to always match them if I can when I'm doing symmetrical kind of work, like those two milled flats or those two drilled patterns. So this way, if I can use common toolpath, I can. I did throw in a little label here. So when we get to the counter spindle, if I don't want to worry about seeing everything that happened up till now, I can jump to that label. This would be my toolpath. So I'm canceling exactly 100, getting my head to some safe location. And then I'm doing my pick and place. There's that workpiece focus command I mentioned. Then we'll do our tool change. And now when we get to our secondary head, I want to use head 2 here. Now when I get to head 2, I'm still programming as if I'm thinking that I'm on my first spindle. So B0 is actually going to give me a B of 180. So when we look at the toolpath, you're going to see that. Or if I do later, I position at 45, it's actually giving me 135, right? But I don't have to think about that. I'm letting the head, so that's one of the reasons why we have this head 1 or head 2 selection, is I can have common values, right? And I don't have to start adding all these extra numbers in play because I'm on my counter spindle or my sub spindle. I say, no, I want my tool 45. I just put 45. Let the control do the math wherever we can. So let's put a quick program stop. I will run the whole thing up till now because you didn't get a chance to see the drilling. We're getting close to the end here, and then we'll open up certainly to some questions. I expected there to be a lot of content with this one. There's a lot of stuff going on when we get into this type of technology for sure. So flipping around, turning, now we're going to mill our face. I'll maybe kick up the speed a little bit. Boom, 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 boom. Mill our flats. I'll slow her down. Now she's going to do our tool change to our drill. Oh, I left the M30 in there. See, I'm doing too many things at once. No problem. So I do this a lot, just kind of staging my M30 as I go. If I'm sent a program from a customer, and I don't want to try to look at the whole thing in one shot, I'll just slowly work my M30 down. The only thing you might have to add is maybe a safety retract or something at times, but it's just a nice quick way to kind of work your way down through a part program. All right, so there's our first flat, second flat, Here's going to be our drill. Drill comes in, drills the 4 holes. There's our transfer. And now if you look, remember I programmed 0, it spun it to 180. So that head 2 handle that. And then I kick her up at an angle. I only told it 45, it really went to 135. Again, we're letting the control kind of handle that. Now it's obviously sitting here because of my M30. I didn't have any kind of clearance, so I'll just jog her up out of the way. Okay, so the only other thing I want to show you guys is dealing with inclined planes. So I'll still use the swivel plane function for that. But when I have to go in and do my inclined planes, now we're going to load up our end mill. And here's just a quick example of where you want to watch that retract strategy when things start swinging around. So here, let's say I position up at that super location. Well, as I swing, right, this is not dynamic as far as it doesn't have TCP command functionality on. So you want to always be careful when you end up at your final orientation to make sure that the tooltip is obviously above the part. Because the last thing I would want would be to be approaching from down below. That's when I can get to a crash situation. So that's just really being cognizant of the total distance from the center of rotation to the tooltip. Because as she swings around, I could potentially leave that tool and not realize it, that I'm lower than the part. And that's usually when crashes can occur for sure. Okay, so milling on an inclined plane. So this is where swivel cycle will now, cycle 100 will now allow me to get on top of. So we're going to create 2 different planes. One is going to be this 45 degree where we mill. I didn't bother going and drilling these holes in this example. And the next one is going to be getting to this angled chamfer so we can drill the final pattern. So when I come in here, I can use my first XYZ coordinates to shift my 0 around. So in this case, I'm shifting it 10 millimeters. Now this is independent of the diameter mode functionality. So this is always going to be, because you're moving the coordinate system, you're not actually positioning an axis per se. So this is all going to be just, if you want to think of it as linear motion. But what this is doing is this is moving my X and Y and Z location. I'm moving the cube around. So this is getting my cube on that corner by shifting it in a positive direction in X. Then I want to tell it what axis I'm rotating about. So in this case, I'm rotating about Y in a positive 45 degrees. When I get to the other side, I'm just shifting it in the opposite direction, doing a negative rotation. But when I ended up with a negative rotation, my axis direction was backwards. So if I want to use the exact same face mill cycle, I can then clock my Z around 180 degrees. These final positions here in the cycle, that would be if I then wanted to shift my 0 along the new inclined plane. If you guys want to get into more description on cycle 800, I did do a milling cycle 800, 2 different ones, one for shop mill and one for G-code, where we really dig into this even deeper as far as each of these variable types. And then finally, we're going to change to our drill, and we're going to do another inclined plane here to get me back, and I'm setting this to basically be my 0. So if I position X and Y 0, that's going to be my new 0. Now, a lot of times what you may not realize, as long as I'm working around the center of my part, I don't have to create a swivel plane for every single hole. I can position with just by spinning my C axis, but I have to be working centrically. So if this feature was off center, it was non-centric, right? It was eccentric. Then I couldn't do this. I would have to have a separate cycle 800 for every single hole. So the final tool path, and then we will open up for questions. Let me get back to Sinutrain. So if you guys got some questions, certainly type them in, and we can dig into this a little further. But our final tool path here, there's our transfer. This was our turning. We're going to do the mill of the plane. So here you'll see I'm using mixed 2 because I'm in a swivel plane, but I'm working on the sub-spindle. And I'm just using some simple facing cycles to machine my 2 flats. There's my 180 degrees out. So this isn't the C, this is the clocking the coordinate system, right? As I move around. And then we're going to load a drill. Now in this case, I actually had 2 different shifts because I wanted to get all the way back on that chamfer. So I shifted it up and over to the start of the chamfer, and then I rotated the coordinate system 45 degrees, and then I slid up that new plane by 7 millimeters. So that was why I was able to actually go to 0, 0 for my drilling. And then you notice, since everything was spinning around the center line of that part, I then just added some C commands to drill all my holes. So my final piece, we'll take a final look at it, and let's run her. All right, so we're going to get past the first section. You guys have seen all this. All right, now let's go transfer. It's going to transfer here in a sec. Oh, mill flat. This would be where I could unsuppress that label and allow me to go right to the transfer. All right, drill. So there's your transfer. Now you'll notice right here, when it gets done with the transfer, it's going to change my display. That was that display command I showed you. So now we're at our B0. We're using head number 2 for our tool carrier. I flip it. Now this is a case where maybe implementing a retract in the cycle would keep me. That was real close. I could have clipped that. That is what we call pucker factor right there. Now we're at an inclined plane, machining the flat. My 0 is staged right here at this corner is where my new temporary 0 is, while cycle 800 is active. Certainly if I cancel cycle 800, it goes back to my global 0. Then I'm going to position a 0 right there. Boom, boom, boom. Drill my holes. And away we go. Cool. So with that being said, why don't we dig into some questions? I'm sure you guys have them. So all right. Will the documentation recording be available for download? So yes, you're going to get a link after the event for, probably won't get it out till maybe Monday or so, but to gain access to the video. So you'll be able to see that. Right now, I'm not posting any of the slides or anything on a common location, but if it's something you guys are interested in, certainly you have my email address here. Shoot me an email. I'd be happy to provide any of the part programs or any of the slide deck or something along those lines for the event. So certainly email me. So thank you. Let me come up here. Expand this. I got some in the chat, some in the Q&A, so you can type them in either spot. Okay, so we have a question. If one of the tools, oh, I already said this already, offset. Yeah, so on mine, let me see if it was commissioned for an offset. So we were worried about, oops, we were worried about what happens if, is this going to pop up now? Come on, gotta wait for it to come back. Well, let's wait for it to refresh. I'll keep going with the questions. But the question was, how do I shift the y-axis for the tool? And we can certainly have a y-axis in the tool field. Would you be able to share this example program so I can cross-reference? Absolutely. Like I said, Alex, shoot me an email. I'd be happy to send you over whatever would be helpful. Why is that doing that? You know, I got so many things running right now. I was just happy everything went through the program. In the shifted plane mode, is there a way to move the G0 in the regular default plane for retracting and engaging before it goes to G1? Okay, so this is a good question, and this can kind of mess you up for sure. So once you've established the cycle 800, and let me go back to the slide deck here to get a visual aid. right? So back here, we have this plane. So now the machine is moving relative to this plane. And there is no way to necessarily suppress this while maybe in a rapid move. It's going to want to move relative to this plane. So in this case, you're going to want to certainly take that into account for your approach and retract to make sure, because you'll think, oh well, I can just do a Z over and it's going to come in the top. No, a Z move, if I'm at a 45-degree angle, is moving relative to this plane. Now you can pre-position the tool closer before instating cycle 800, but keep in mind things are going to need to rotate down, so that can be a little tricky. Now, one of the things that I didn't show because we didn't have it turned on in this machine, but you can start to look at when playing around with these inclined plane orientation changes, is a function called tracking. So if you are, let me see if this thing decided to come back. It did not. Oh, maybe it did. If your, oh good. If your machine is set up for TCP functionality, then cycle 800 can actually have an extra variable here for tracking, tool center point tracking. And then as I induce the swivel cycle, it will maintain that center point. So that may be a scenario when you're doing a lot of inclined plane stuff, if you want to be able to orient while staying close to the part. But no, unfortunately, there's no way per se, once the plane has been established, to then suppress the motion in rapid. Dave said, do you have to turn on cutter comp to compensate for the tool nose radius, or is it covered manually with the cycle 800? So cycle 800 does not do anything for cutter compensation per se. I'm positioning to the tangency point, but if I'm machining, a radius, then I still would want cutter compensation to be on. The cycles may automatically apply cutter comp if you're using our cycles, but if you're in straight G code, no, you would still want to induce G41 or 42 and have your normal cutter comp scenario. So the cycle 800 is managing the tool orientation and the tangency points based on that orientation. But once I start moving the tool on my curved shape, I still would want to have cutter comp to be active. You mentioned using STL files for workpiece files. Is this possible to import my casting models to watch a better simulation than a pipe or a cylinder? So that's a good question. Now, by default, our standard simulation does not support STLs, but if your machine was commissioned for, let's see if I'll get back in. If your machine was commissioned for this collision avoidance model, like I'm using here, it would be possible to bring an STL in there, but you would need to have a Sinutrain machine, or on your real machine would have to have the collision avoidance functionality turned on. So if you don't have that, and how do I know I have collision avoidance? Well, other than getting this machine space model, when I'm back here in jog mode, you'll actually get, see if she wants to come back. My PC is not happy. There it goes. You'll see these little sunglasses. This is always a dead indicator that your machine was set up for collision avoidance. If you have collision avoidance, then we can start to do a lot more with bringing in STLs. But by default, the standard simulation and editor does not support STLs. Okay. Love the machine models. How do I get them on my Sinutrain? I'm glad you asked, Steve. That's a great question. So by default, Sinutrain has this ability of creating what we call a digital twin. And it's generally going to be an exact duplicate of how your machine looks in space. However, we do have a new service that we're providing specifically, typically to OEMs or importers or dealers, where we can partner with them and we can build a custom, what we call set file or digital twin machine that can run inside of this Sinutrain software, that can have a full machine space model. So really gives you a nice conceptual of what's going on. So it's kind of like, we like to call it the poor man's digital twin. You get to some of these digital twins, we do a lot with NX or Vericut's another one that we do some real high-end digital twins. They're great. They got super high res, all sorts of capabilities, but it's pretty pricey. So from the Sinutrain side, you can get into this concept and have really as close to a real machine running virtually. So what I would say, if you're interested in trying to get one of these, get Sinutrain set up and have a duplicate of your machine, if you're an end user, it's hard for us to usually work directly with the end user, because one of the big things we need is all the machine models to be able to build it, right? So if those aren't available, then it makes it a lot easier to work directly with the OEM. So I'd say if you're an end user, reach out to your OEM or your importer, whoever you're dealing with that you bought the machine, to see if they have, if they're already partnering with us and they have these machine set files available for your model. And if they don't, direct them to talk to one of us, and maybe they'll want to start taking advantage of this service. Okay, let me see if I missed any. There were a lot of great questions from the audience. I think we covered it all, and we're a little over, but I see everybody hung on. I certainly appreciate that. Hopefully you guys found this real interesting. Again, feel free to reach out to myself or any of my colleagues for support in the future. And if you'd like any of this information, shoot me a text. Oh, we got one extra question that came in from Adrian. Can you still use the different commands like trans and rot, etc. in a Milturn? Absolutely, for sure. The thing with trans and rot, when you go to actually align the tool, you're still going to need a function that's going to support it. So trans and rot are moving the zero around. But when I want to induce a rotation, typically you would then use Traore for that kind of functionality. You can do that in a turn mill for sure. It just tends to be a lot easier to drive it through the swivel cycle. All right, great. Darren was thank you guys for showing up. I always appreciate it. And if you have any questions, reach out, and I look forward to talking to you next one. All right, we'll see you in a few weeks. Thanks. Bye-bye.